Okay, so today I'm going to present you basically the results of the PhD of Arnold Ngabasare, who was here up to 2021. Now he's a postdoc in Cape Town. Okay, it was my first PhD in Lima. And basically all I present is his PhD in collaboration with Yorgos and Olivier in the lab and Haris Kokos, who is in Cape Town. Okay, so let's forget the title for now. So what was the main idea? So the main idea was twofold, let's say. First, we had in mind mechanical lattices. So I show here 3 examples. So on the left, I show what we say granular crystal, which is a lattice composed of macroscopic objects in contact. Okay, and this is in fact from the thesis also Floriana, also in the lab. Another system had in mind was what we call now flexible elastic metamaterials. So let's say macroscopic objects again that they are combined with some elastic beams, for example. And this is a Lego structure, okay, an elastic beam connecting the Lego blocks. And also another system, we're not going to talk about that, but it exists. It's origami lattices. Also, it's a mechanical lattice, okay, with many degrees of freedom that is able to propagate waves. So why this kind of lattices? First of all, we're interested in nonlinearity. And so these kind of lattices are proved that they are able to have strong linearity due to geometry mostly, and also due to forces. And also because since these structures, we can build them and we can change the characteristics of the medium. Let's say it could be different material, or also the geometry again. We can tune the dispersion relation of lattices, okay? So they're tunable structures. Now that's the first theme, let's say, so mechanical lattices. And the second theme we're interested here, it is Anderson localization. Okay, so just fast for now, I will show more later. What I mean by Anderson localization here is the fact that, let's say you have a lattice, you put disorder, and then the modes of the system become localized. Okay, so that's, let's say, very fast explanation of what I mean here, Anderson localization. And since the modes are localized, usually the energy cannot propagate long in the system, it remains localized. And the question is, what happens if we put nonlinearity in the system? So does the localization persist or does it destroy? Okay, and that would be the main thing. And so here I just put 3 reviews of Anderson localization in low-dimensional systems, so 1D, as the ones I talk here. There are a lot, a huge amount of work on that. And the idea here was to combine this, let's say, more theoretical works with some systems that could be done on experiments, which is the mechanical lattices. So 90% of the talk will be theoretical, although we have in mind these experiments. And only at the end, I will say that now we are trying to go a bit to experiments. Okay. So, okay, I will make a very small introduction of what I mean Anderson localization, how we study Anderson localization in these particular works. Then I will talk basically about 3 systems. One, it is this granular lattice I showed before, okay, in the presence of disorder. And what we're going to do, we're going to compare the results from this model, which is highly linear, with results from the Fermi-Class-Taylor model, which is very universal model for nonlinear lattices. Okay, we're going to see differences between the 2 and some interesting results. Then I'm going to show results about so in the first case, we're only going to take into account displacements of the mass system. Okay, so 1 degree of freedom per site. Then we're going to move on to something a bit more realistic, which is 2 degrees of freedom. And we're going to try to see the effect of rotations in this kind of lattices. And again, the presence of disorder and nonlinearity. And the last part will be about this Lego structure I showed before. So the model will be describing that Lego structure. When once again, we will try to see what is the effect of the presence of 2 degrees of freedom, okay, and disorder, okay, and then some perspectives. So let's go with the motivation. So let's start with the simplest scenario in this talk, which is to consider a lattice of masses, okay, connected with springs. And this is described by Hamiltonian where the mouse works. Yes. So where we have the kinetic energy of each particle here. So P is the momentum, M is the mass. And then we have here the potential energy, okay, for each particle, where K is the stiffness connecting the particles. Okay, that's a very well-known problem. Let's say we can find the modes of the system. And here I just show these modes. Probably everybody knows this kind of diagram. On the y-axis, I have the frequency normalized. And on the x-axis, I have the number of modes. So here is a lattice of 1,000 particles. So just to remind, I also show three kind of modes. One mode at low frequencies, so mode number 2, let's say. One mode in the middle of the band structure, and one at the end. Okay, these are waves, extended waves. And of course, the higher frequency, the more oscillations I see. Okay, nothing special for that. Now let's do something. Let's put disorder on the mass. What do I mean? So we have this kind of drawing sometimes to remind the system. I mean that I take the masses to have different values, okay? Randomly chosen. So what do we see? So first, let's look at the spectrum. This is an example of one realization, so one disorder. I find the spectrum, I show it on the right-hand side. What do we see? Let's say we see that the low frequencies, so here, the spectrum looks to not be changing so much, in some sense, okay? While in the high frequency regime, here, we see, for example, that the highest frequency before it was 1, and for the same that's now going up to 5. So I've increased the band, let's say, and the shape has some particularities. And let's look at the modes, which is most important. So let's take the first mode, which is at k equal 2, so the lowest mark. It looks almost the same as before. In some sense, it doesn't see the disorder, okay? It's an extended wave, and it looks the same as the no disorder. However, when I go even in the middle of the band, and especially at the end, the modes are localized. Okay, so this is two examples of the modes. They are randomly localized anywhere in the system, you don't know a priori. Okay, and then, for example, here is something with about 50 masses contributing to the mode, and the last one is 2 or 3, so very localized. By the way, here I'm putting strong disorder. Let's say the smallest mass with the highest mass here, they have a ratio of 5. Okay. Okay, so that's the first thing to remember here. When you have this kind of system, we put disorder, many of the modes become localized, some of them low frequencies, they're extended. And in fact, so this is some theoretical results that they show that in this particular system, there will always be square root of n extended modes. And what I mean extended, I mean modes that have a width at the size of the lattice. Because it's a finite lattice, it could be 100, 1000. This square root of n gives you this quantity. Okay. Now something a bit different. So before we talked about the mass spring system, the usual one, so mass connected with springs. There is another example where we have still a mass spring system, but we also put an on-site potential. You can imagine that we put another spring connecting it to the ground, here to the roof. Okay. Why? And then what happens is that, okay, we almost have the same equations and the same Hamiltonian for the system, plus this term here, taking into account this extra spring. Okay, we can solve again the problem. So now what happens is that the spectrum is a bit different, or say quite different. It's here. So y-axis frequency again, and the x-axis is a wave number. What we see here important, the most important, is that now there is no propagating modes around omega equals 0. Okay, there is a gap. So the first propagating mode is already at a finite frequency. Okay, you have to remember this a bit. Is the main difference from before. Okay. On the other hand, if we just look at the modes, how they look, they are a bit the same as before. This is the periodic case, no disorder, just adding the spring. What happens if we put disorder? A bit like before, the spectrum looks different. Okay, you have a lot of modes disorder. But now there is a huge difference here in this particular problem. The huge difference is that due, in fact, to this gap, now all the modes are localized. Okay, so here I show modes. So this is the same as before, 2, 500, 1000, and they are all localized. Okay, there is no mode that it is extended as before. And in fact, it has been shown that this, I call it Klein-Gordon because it is the Klein-Gordon lattice in the nonlinear case, but it's a mass spring system with an extra spring. It can be mapped exactly one-to-one with the Anderson 1D model. So in fact, everything is known that for the Anderson model in 1D, which is that every mode is localized depending on the strength of the disorder. It is one-to-one mapping. Okay, that is for the Klein-Gordon, not for the usual mass spring. Just remember. And all modes are localized. Okay, so now just to, because I'm going to show a lot of figures after that will look identical, and just to explain what they are. Okay, what I'm going to be doing mostly in the numerical simulations I'm going to show, it is the following. We will imagine a lattice. We go in the center of the lattice usually, and we excite one particle. That will be almost everything I will show. Okay, and then just to visualize a bit what it does. So here is a case of a periodic chain. I go in the center, I excite, and I show the energy per particle and the particle number. Okay, so let's go again. What I do. So I excite in the center, there's waves propagating, there is two fronts, left and right symmetrically, propagating like that, okay? And the wave is spreading in the lattice. That is in the periodic case, okay? Now let's see the example when I put this order. It looks a bit the same, but now we see some differences. So a lot of energy remains in the center, as you see, and then there is two propagating edges, okay, going away. And these are the ones that are spreading the energy in the system. Okay, so we're talking a lot about energy spreading. It's exactly these edges that spread the energy. But the difference here, really, as you see, is a lot of energy staying in the center. So now to see that, not in a movie because it could be a lot of time to always see movies, I will be showing contour plots like that mostly, where the y-axis is time, x-axis is the particle number. Okay, and then we see the same thing as before. We just see the front propagating. In fact, this propagating front, it propagates with the effective speed of sound at the low frequencies, which is 1 here normalized. So we just propagate it like that, spreading the energy. And this is a periodic case, so it's homogeneous. And in the disorder, now we see that we have, as before, the propagating front, which propagates with the same speed, in fact. So the effective speed at low frequency is the same. But we have a lot of energy staying in the system. Okay, so what I will be trying to do from now on is to quantify a bit this energy spreading in the system when we are disordered or when we are homogeneous. Okay, and the main tools I'm going to be using is what I call the participation number, which is here. Here, Hn with small h, it is the energy per normalized energy per particle. And what does it do? This participation number, it tells you at any time of to work for modes or during propagation, it tells you how many particles are participating in the motion. So for example, if I have only one particle oscillating and the rest are sitting, this guy has number 1. If everybody is oscillating, that's number n. And the other measure I'm going to be using is M2. So I will call it, this is the second moment. What does it measure? It measures, you put a wave packet, it spreads. So this quantity measures the spreading of the wave packet. Okay. So imagine that when I put one particle, it's a wave packet, that's very localized, and then it spreads. I'm measuring how fast it is spreading. And many times I'm going to be assuming that the spreading of M2 has a form of an exponent of time. Okay, it's a polynomial of time. And this beta would be something that we'll be using a lot to characterize the motion. For example, of what we've seen before, homogeneous case, participation number starts from 1 and just increase linearly, because all the particles will participate at the end, should go to n. And then this beta, which tells me how the spreading is done, it goes up to a value of 2, and one can show that 2 corresponds to ballistic propagation. It means that you just have plane waves propagating, traveling with the speed of sound. Okay, this is the maximum spreading you can get in this case. Now, if we put disorder, things change. First of all, participation number is finite. So at some point and after, only some particles are participating in the motion. And most importantly, the spreading now also reduces to a lower value. Okay, so for the mass spring system, I said before, there is some analytical results from these 2 papers, in fact, one below and one more recent, that they are predicting these values for the disorder case. So we call anything below beta equal 1 subdiffusive, and everything upper 1 super diffusive. And here, what is funny is that if you start with a kick So let's say momentum excitation, you get a super diffusive behavior. But if you start with a displacement, you end up with a sub-diffusive behavior. So this game of initial conditions and how energy propagates, something I want to explore here in general. Okay, and now let's go to nonlinearity. So I will go faster in this review because anyway, it's not my field. But regarding nonlinearity, so the question is, what does it do, nonlinearity, to these systems with respect to this energy propagation? Okay, so a lot of studies have been done, mainly in the DNLS. So this is the Anderson model with a nonlinearity, which is here, this cubic nonlinearity. Okay, it is called the discrete nonlinear Schrödinger model because it is a discrete Schrödinger equation with a nonlinear term, and also the discrete Klein-Gordon lattice. Okay, a lot of work have been done for these two, and in fact, they are kind of summarized in this diagram. Here, the y-axis is the nonlinearity strength, so if I am very nonlinear or not, and the x-axis is the disorder strength. Okay, and in general, for both, the people have found, so I put reference here, that there are mainly three regions. One, I call it localization, so it's here, strong disorder, less nonlinearity, where you have mostly localization. Then there is region 2, when you have sub-diffusive spreading, as the one I showed before. You have some localization of energy spreading, okay, but sub-diffusively. And then there's this region 3, when you have something in between. What does it mean? It means that you have some modes that remain localized in the lattice, but some of them are spreading the energy, okay? And that is the region 3. So that's mostly what has been done up to 2011-12, maybe, about nonlinearity and disorder. Of course, with other references. Then there is, regarding the FPU model, there were some results, numerical, showing that there is no clear behavior of what happens for the energy spreading at the end. And it is this paper of Lepri, Schilling, and Audry. And then also, when we started working on that, we did the same study, so the study of increasing nonlinearity in the presence of disorder. And we did that in the granular model during 2016, also partnered with another team. And we found out that in this case, what you see is that when you increase nonlinearity, in fact, you can go back to ballistic behavior. What does it mean? You have the homogeneous lattice, it is ballistic. You put disorder and you are linear, energy is propagating sub-diffusively, so slowly. And then you put strong disorder with this model, really strong disorder, you go back to ballistic propagation. Okay, so that's what was known. So let's go to something more particular. So this is the first work of Arnold. Let's go to this granular lattice model. So once again, we have momentum, so kinetic energy and potential energy. Here, it is a characteristics of the Hertzian model for spherical bits in contact. Okay, what you need to know, in fact, for the model is that okay, we have a stiffness, we have the power law, which is nonlinear contact law, and we have this plus sign. We'll discuss a bit later, which means that when two bits are out of contact, there is no force. So it means that when the distance between two bits is more than this delta, which is the overlap, there is no force. So this should be a strong nonlinearity, meaning that this term goes to 0. Okay, that is the plus sign. What is interesting here is that we can do some approximation for small amplitudes, and we can derive the FPU model from the granular. That's for the inspiration to compare the two. Okay, but this is more a weakly nonlinear model with respect to the granular. So what was the idea here? We said, okay, let's make a lattice finite and then see what happens to a localized mode when we increase the amplitude. Okay, we find localized mode, we increase the amplitude and see what does it do. And then we want to compare the results with the FPU. So what we did, we take one realization, disorder meaning that the masses are different. What I change here is the radius of the bits. And then that is a spectrum for a finite lattice of 40 particles. So frequency, number of modes, okay? And then we found one mode, this one here, 32, I think. And then it is a mode very well localized in the center. That's the profile of the mode on the right. Okay, it's very localized around the center. And the idea is that we're going to excite this mode with more and more energy, okay, and see what happens. So let's start with two different energies exciting this mode. How do I control the energy here? I just take the mode I put it as initial condition with a bigger number. Since the problem is nonlinear, I'm putting more energy to the system. Okay, so this is two different energies, 0.5, 1.8. And what do we see? So time again, position of the particle, and what is plotted is the energy per particle. So here, I put all the energy in the central node, central particle, and it remains there 4 times 10 to the 5. So it is localized. It reminds me of Anderson localization. Everything stays there. Although the system is nonlinear always. On the right-hand side, I see that after some time, so there is initially there is some waves propagating at the edge, there is some intermediate region, and at the end, it looks like the energy is everywhere. So the energy has spread, and it's all around the system. Okay, so for now, it's a bit what we expected, in fact, nonlinearity to break localization, and here it is a proof that it looks like that. But there's something more funny here, because many times this spreading with nonlinearity, it is associated with chaos, meaning that chaos, like coupling of trajectories in phase space, okay, it's the reason at the end, and thermalization they call it, the reason to excite all the modes of the system. And we wanted to check if there's a point here. So I will not go to details of the Lyapunov. What we measure is the Lyapunov exponent. It is a measure of if the trajectory is chaotic or not. And just to tell when I'm showing this kind of plots, here is the Lyapunov exponent as a function of time. Normally, if the system is not chaotic, this Lyapunov exponent has to go to 0 with a slope 1. That's important. Usually, they say it is exactly 0 at t equal infinity is not chaotic. Here we cannot go to infinity, but it has been shown that if it goes to 0 with a slope of 1, the system is not chaotic. And this is a dashed line here. So the two red lines correspond to these two dynamics I showed here. What we see is that initially it looks like it's going to 0, but then the Lyapunov exponent takes a finite value for both cases. So here, what we conclude is that they are both chaotic. Okay, the one with high energy has a bigger Lyapunov exponent, but doesn't change a lot, is more chaotic. But the funny part is that in this case, we have shown that chaoticity alone is not sufficient to see spreading, because we have a mode which is localized and chaotic, but remains localized for times 10 to the 5. Okay, while on the other hand, it's true that chaos and nonlinearity is able to spread the wave. So that's the first result. Here, I think I will not go. Not. Now, let's see what happens. We'll do exactly the same, not for the granular chain, but for the FPU system. Okay, again, low energy, we see that the particle remains localized as before. I put the energy in the center, it stays in the center. High energy, it starts to spread. Looks okay, not so different from the granular chain. But what was surprising, we increase the energy more. So here it was here it was already 2.9 already spreading. Then we increase the energy more, H equal 4, and it remains localized. It's going back to localization. So this is for the FPU. And then increasing more, we see again that the wave packet spreads. So this is something we are not still understanding why, but we have an idea because this FPU model, it is not so far from being, let's say, integrable. It is not integrable, but it has the reminder of trajectories that are kind of periodic, okay? And this is normally due to that, but it's something that is open to understand in this case, okay? But it is fine to show that you put energy, you are localized, then you delocalize, and you go back in. And in fact, this is also we'll show now. It's also, you see, projected in the two-partition of energy. So, two-partition of energy, we want to see how many of the modes are excited at the end. So we have n modes of the system. We put 1, and at the end, we have to see how many modes are excited. So to do that, we use this, what is called the spectral entropy. Okay, it's defined here, where UK is again measuring the energy. It is a normalized quantity which takes the value 1 if only one mode in the system is excited. It takes the value 0 if infinite modes are excited. Okay, so let's go to the granular chain for small energies. So what I show here, it is spectral energy. So it starts with 1, it almost stays 1. And what I show here, it is a projection of the modes. So I have n modes, so k modes, a function of time. And the color is how much strongly this mode is excited. So here we see that only one mode is excited. In fact, it's the mode that we have put it. And at the end of the simulation, it is the same. It's the only mode excited. Okay, let's go to a higher energy. You see that slowly other modes are exciting in the system, the low frequency modes, in fact. But still, I don't have a lot of modes participating here. But after a critical point, whatever energy we put, so this is high energies, this spectral entropy goes to almost 0. So in fact, it's not exactly 0. It's a finite value which is predicted for a finite lattice. Okay, and this is a dashed line. And from now on, it doesn't care of the initial condition. Whatever you put, it will always at the end excite all the modes. So that we call it equipartition of the model at the end for the simulation. Then here it's the same for the FPU, but for the FPU, we see once again this recurrence. Okay, we start with one mode only. We go to something close to equipartition. We increase the energy. We go to something that is mostly one mode, and once again. So this is an interesting feature we need to study more. This part, okay. Let's go to another system. Okay. So everything I did up to now was 1 degree of freedom per lattice set. Now we're interested in something, let's say, closer to experiments or closer to realistic macroscopic structures. And at least we said that since many works now focused on taking into account high degrees of freedom, we said let's do that in the same context. Okay, three systems that we had in mind is again the granular chain, but taking into account the fact that the bits can rotate. Also, these Lego lattices that they are composed by crosses with a small connecting beam that, of course, they can rotate and be displaced. And then we started by simplified model, which is here, which is taking 2 blocks, masses, that they're able to displace in some direction, but also due to a bending force, they can rotate. Okay. So now the system I'm going to be solving is a coupled system, 2 degrees of freedom. Each particle has a transverse displacement, and each particle has rotation. And this is the couplings. Now, difference from before, I have 2 kinds of couplings: the transverse displacement, stiffness, and the bending stiffness. Okay. After taking into account, this is the model. Okay, it is something. Most important is the band diagram. So what happens now? First of all, we have 2 degrees of freedom. We have 2 bands, different from before. Second difference is that these 2 bands are coupling the 2 degrees of freedom. So every mode is not only displacement or rotation, it's both. Okay, so this makes it a bit more interesting. So here what I will be doing, I will be keeping constant the shear stiffness, and I will be changing the bending stiffness. Okay, why? Because in that way I can strongly change the band diagram. In fact, by just changing, so K2, it is here. Okay, just by changing K2, I can transform the band diagram quite a lot. Okay, and it is an extra parameter, and it's what I said in the beginning, is the tunability I can have to the system due to that. So I want to explore a bit what happens in different cases. Okay, once again, let's put disorder. So here is the no disorder spectrum. Here it is with disorder. Okay, what we see is that first, we have 2 bands in the periodic case, in the homogeneous case. If we put strong disorder, first of all, we close the gap. So we fill the gap with modes. So now it looks something like that. Okay. Second, it looks a bit like the FPU because the low frequency modes, they are extended as before. The high frequency modes are localized. Okay. So we expect to see this competition between the 2 as we do some simulations. Now the idea was the following. So here I'm linear. So let's try to excite the system with 2 different ways, only with transverse or only with rotation, and see if there's a difference. Okay. So what we find is the following. So here I show 2 simulations, initially displacement or initial rotation. What happens is that, and I show the participation number. So what is funny is that now the system depends a lot, either if you start by displacement or rotation, on how the energy is propagated and how many particles participate. Okay, so that's one funny thing, because just by the same system, disorder, you change the initial condition of the particle and you change how the energy propagates. Then the famous exponent beta I said before, it is found to be different and subdiffuse it for rotations, while superdiffusing for displacements. So already it is faster than the corresponding mass spring system. So the rotations are adding a lot to the system. So, okay, there is 4 different regions we can find, and every time we find some different value of the asymptotic energy propagation. Okay. So the question is, what really happens? If you can use this K2 to see more interesting stuff. First of all, what we see, imagine, I'm always doing the same, like exciting in the center, seeing the energy provided. Always the same thing when I'm showing. What happens here is that due to the fact that this branch here, it's very low and it has very slow modes, the propagating modes are very slow. What we see is that there is a region in the beginning where everything looks localized. For example, if you stop the simulation on 10 to the 3 or 10 to the 4, you will see that it is completely localized. But it's not true, because this is due to the fact that the modes that are propagating are very slow. You have to wait long enough such that you see propagation in the system. Okay, then we say, okay, let's imagine an extremity and let's cut off the bending stiffness, make it 0. And then when it happens, it's interesting because we go back to the Anderson model, and if you put the energy in the center, it will remain in the center forever. So you recover Anderson localization just by tuning the bending stiffness. Of course, you argue putting the bending stiffness to 0, it's a bit artificial, but you can see that going to very small values, you'll be able to localize energy in the center. Note that when I do that, I don't decouple the system. They are still coupled. I'm just removing one parameter. Yes, just in time. So then another thing we wanted to check is, since all the modes are the 2 degrees of freedom, we wanted to see if the energy, we said energy, but we don't know where it is stored. Is it stored in the rotations or the displacements? And here we made a check of how the energy is distributed depending on the degree of freedom. And what we find is that, again, it depends a lot of how you start the excitation. Okay, so for example, here I'm showing the energy stored in the center when I excite with rotations. So I excite the rotation, I see energy propagating and something remaining in the center. And what remains in the center is mostly rotations. So most of the energy is stored in the rotational degree of freedom. On the other hand, if I start with transverse displacement, so here, what I see is that the energy stored in the center is more equal. So let's say it's close to 50. So this is the amount of energy, and the color is rotation or displacement. Okay, and you see again this strong dependence of how you excite the system, which makes it interesting. And this is the same idea, but for the edges. The edges are different. The edges are always more populating the transverse displacements. And in fact, this is a bit expected in some sense because of the dispersion relation. So the edges are usually due to this low frequency modes propagating, and they are red. They are usually just displacements. Okay, so let's go to the last part, third system we studied. So this is the Lego structure here, composed by crosses, okay, which are connected with a film, a thin film. Okay, why is this interesting? Because this system is highly nonlinear, first of all, for our case. Because of the geometry of the system and of this film, it is highly nonlinear. Now we have 3 kinds of stiffnesses: bending, shear, and stretching. And the model, okay, it is here. It's not to discuss about the lot, but to say again, I have the displacement of the process, okay, u, and the rotation, couple degrees of freedom. And here it is nonlinear with a strong linearity, which is sinusoidal. Okay, then we will use that. So linear limit, once again, interesting in this model, in the linear limit, they are decoupled. In the linear limit, the rotations don't see the displacements. And this is the dispersion relation of each one, okay? And what is funny is that one of them, the red, so the displacement, it looks like the mass spring system, while the other one, the rotation, which is the blue, it looks like the Klein-Gordon. So we find the optimal system that is combining exactly the 2 one before. And they are uncoupled in the linear limit. In the nonlinear, due to the nonlinear forces, they become coupled. So the idea here was to start exciting the system and see nonlinearity, what does nonlinearity do? So first, just to recap before, displacements follow mass spring system, everything I said in the beginning. Rotations follow Klein-Gordon system. Anderson localization, spreading, okay, in the presence of disorder. So this is the localization part here. Sorry, this is the spreading here, and this is full localization. Now, what happens when we couple them? So we start exciting the system, again in the center, with some energy. So what we see first is that we have localization, participation number equal to a number, so to a finite value, sorry. And at the same time, this exponent beta, which shows if you are spreading or not, has some behavior which is not clear. It doesn't saturate the value. Okay, we cannot conclude a lot of stuff from here. But what we can see is that it has a tendency to go to 0, and then it evolves again. So what happens here? So in fact, it is once again the interplay of the two different degrees of freedom. What happens is that we excite everything. So we excite both degrees of freedom. But since we are strongly disordered, the Klein-Gordon part remains localized in the center. So it's here that I show the energy as a function of space. So the Klein-Gordon part remains localized in the center, while the, let's call it FTU, the mass spring part is going away. But once again, this part, it is slow. It propagates with a slower speed. So in fact, what I have here is a transition between everything looks to become localized because the main object, it is a localized rotational part. And after some time, energy propagates due to the displacement. Okay, and this in fact here, this coupling is induced by nonlinearity. If it was linear, fully linear the system, there would be no coupling. So this small nonlinear coupling is able to induce this transition. Okay, it's explained here more. And then what we have done, we have, so this is supposed to be an energy diagram with increasing energy. So now I have an energy which is quite strong. And in fact, what we have found is that by increasing the energy, we go slowly to ballistic propagation. What does it mean? Again, from just energy going subdiffusively, by increasing nonlinearity, we go to almost as there is no disorder. The energy propagates as there was no disorder. It is important, instead of saying ballistic, to say that. Okay, nonlinearity is able to make the energy propagate faster. So, okay, let's go to just final. So everything I said before, it was what was done during the PhD of Arnold. And now something we are trying to do is, with these 1,000 particles, to go to experiments. Well, not true, let's see. What is the question is, can we see something experimental? Okay, so we started collaborating with Florian. At this point, when he's able to print structures like this. Remember the model I showed of cubes connected by beams? So this is a 3D printed lattice, okay? And in fact here, if you watch closely, there is some, you can vary the value of these connecting beams, okay? You can put disorder by changing the beam size, okay? And for example here, if I'm not mistaken, so this is the values that can be printed, is of the order of the radius of the beam of the order of 2 millimeters or smaller, and you can play with these values to induce disorder on the couplings, okay? And then the masses are being played, the role of masses is played by the circuits or something else you can really print. So what is the challenge here? The main challenge is that the system is finite. So before I was going to 1,000, 5,000. So the question is, if you want to measure this M2 or these exponents, is it possible with a finite structure? So here I show a simulation for, so it's 100 particles, okay, here. But we see that, and this is the famous spreading parameter M2 and the exponent. And what we need to see, is it able to reach the value of homogeneous here, the value of 1 at a finite time? And the answer is it is, okay? So for the moment, 100 maybe looks a bit big, although possible. But according to simulations, here they are with no loss, with nothing, we can observe something, let's say with something like 50 particles. Of course, everybody would argue, what about losses? That's why we're very small. So, of course, so we have some modeling from the experiments that Florian has performed. And in fact, it seems that the stronger losses are at the connections, at the beams, okay? And in fact, they are modeled with something we have here. And we have done already some simulations, which are not so pessimistic in the sense that still, in this case, exciting the system is still homogeneous. for the moment. We can see that what we need to measure, which is the spreading parameter gamma, is possible to be done for a chain of 100 particles. Okay, so we will try. Of course, it's a challenge. It's not going to work. The challenge here is to make the optimal setup that will be possible to measure these quantities. And the funny thing is that here, indeed, we can excite really either rotations or displacements alone and to see the difference. Okay, that is the dream. Okay, let's summarize. So what we have shown is that among different stuff is that first of all, we can have localized chaos if we use mechanical lattices nonlinear with disorder. We have seen that nonlinearity is able to induce energy equipartition, so to populate all the modes of the system. Also, we have seen that when we add degrees of freedom to the system, we have different asymptotic behaviors, okay, depending on the particular model we are studying. And also, we have seen that it is possible to control the energy transport just by tuning the different degrees of freedom. So the most interesting part here, I think, is this one, that if you are able to, let's say, control energy propagation in a disordered lattice just by tuning some parameters. And something of what is to be done next. First, we want to understand these asymptotic values in the theory, how we can explain it theoretically, because this is something open. It's only done for the mass spring system, the simplest one, and not for this case. Of course, we want to see the experiments, and that's something we are on to now. And even for furthermore, we want to study other models which have strange, let's say, spreading behavior and energy. One model that we found is this one here that has the form of a fourth order discrete derivative. And in fact, this model seems to be mapped directly to a tight binding model with correlated disorder. So correlated disorder means that I'm putting the masses, for example, always in pairs. And this correlation induces energy spreading of particular form. And it seems that this model can be directly mapped to here. So we want to check this opportunity. That's it. Not too late.